Quantum mechanics. Quantum mechanics is the branch of physics that deals with the behavior of matter and energy at the smallest scales, atomic and subatomic levels. Unlike classical physics, quantum mechanics reveals that particles can behave like both waves and particles, leading to strange phenomena like superposition and entanglement. It's the foundation for modern technologies like semiconductors, lasers, and quantum computing. Wave-particle duality. Wave-particle duality is one of the core concepts of quantum mechanics. It states that particles like electrons and photons exhibit both wave-like and particle-like behavior depending on how they are observed. For instance, light behaves like a wave when it spreads out in interference patterns, but like a particle when it interacts with matter in discrete packets called photons. The double-slit experiment. The double-slit experiment demonstrates the wave-particle duality of light and matter. When light or electrons pass through two slits, they create an interference pattern on a screen, as if they were waves. But when observed, they behave like particles, landing on the screen in individual spots. This experiment challenges our understanding of reality, showing that observation affects behavior. Heisenberg's uncertainty principle. The uncertainty principle, formulated by Werner Heisenberg, states that it is impossible to know both the position and momentum of a particle with absolute precision. The more accurately you know one, the less you know the other. This isn't due to measurement limitations, but is a fundamental property of quantum systems, introducing randomness into the behavior of particles. Schrödinger's cat is a thought experiment designed by physicist Erwin Schrödinger to illustrate the paradox of quantum superposition. A cat is placed in a box with a poison that could be triggered by a quantum event. Until the box is opened, the cat is both alive and dead simultaneously. This highlights the strange nature of quantum systems, where objects exist in multiple states until observed. Quantum superposition. Quantum superposition is the ability of particles to exist in multiple states at once. For example, an electron can be in different places simultaneously. It's only when measured that the particle chooses a single position. Superposition is central to quantum computing, where qubits can hold multiple states, vastly increasing computational power. Quantum entanglement. Quantum entanglement occurs when two or more particles become linked so that the state of one instantly influences the state of the other, no matter the distance between them. Einstein famously called it spooky action at a distance. Entanglement plays a crucial role in quantum computing and quantum communication technologies, as it enables faster-than-light information transfer. The quantum wave function. The wave function is a mathematical description of a quantum system, representing all possible states a particle can occupy. It gives the probability of finding a particle in a particular state. When a measurement is made, the wave function collapses, and the particle is found in a specific state. The wave function is at the heart of quantum mechanics and quantum theory. Quantum tunneling. Quantum tunneling allows particles to pass through energy barriers that they shouldn't be able to, according to classical physics. For example, an electron can tunnel through a barrier, even if it doesn't have enough energy to overcome it. Quantum tunneling is used in technologies like scanning tunneling microscopes and plays a role in nuclear fusion within stars. Quantum decoherence. Quantum decoherence is the process by which a quantum system loses its superposition and behaves more classically when it interacts with its environment. This explains why we don't see superposition states in our everyday world. It's one of the main challenges in building stable quantum computers, as they must remain isolated to maintain quantum states. The Born rule. The Born rule, proposed by Max Born, provides a way to calculate the probability of finding a quantum system in a particular state. It states that the square of the wave function gives the probability of observing a particle in a specific location or state. This rule bridges the gap between quantum mechanics and the measurable outcomes we observe. Planck's constant. Planck's constant is a fundamental constant in quantum mechanics, symbolized as h. It represents the smallest possible unit of energy exchange in a quantum system. Planck's constant plays a key role in defining the quantized nature of energy levels in atoms and is central to the equation for the energy of a photon, E equals h, when u is the frequency of radiation. Quantum field theory. Quantum field theory, QFT, is the framework combining quantum mechanics and special relativity to describe how particles and forces interact. In QFT, particles are excitations in underlying fields, like the electromagnetic field for photons. It forms the basis for the standard model of particle physics and helps explain phenomena like particle creation and annihilation. The quantum harmonic oscillator. The quantum harmonic oscillator is a model describing the vibrations of particles in a potential well, like a spring or vibrating atom. In classical physics, a harmonic oscillator moves smoothly, but in quantum mechanics, energy is quantized, and the particle can only exist in discrete energy levels. This model is fundamental to understanding molecular vibrations and quantum states in atoms. The Pauli exclusion principle. The Pauli exclusion principle, formulated by Wolfgang Pauli, states that no two fermions, particles like electrons, can occupy the same quantum state simultaneously. This principle explains why electrons in an atom fill distinct energy levels, shaping the structure of atoms and the properties of matter. Quantum spin is an intrinsic property of particles, like electrons, that resembles angular momentum, but isn't related to actual physical spinning. Particles have a spin quantum number, which can be up or down. Spin is essential in explaining magnetism, particle interactions, and the behavior of particles in quantum systems like quantum computers. Quantum states and qubits. In quantum mechanics, a quantum state describes the condition of a particle, such as its position, momentum, and spin. A qubit is the quantum version of a classical bit in computing, capable of existing in superposition, both 0 and 1 simultaneously. This ability allows quantum computers to perform many calculations at once, revolutionizing computation. Quantum gates are the building blocks of quantum computing. They operate on qubits, manipulating them to perform computations. Unlike classical logic gates, quantum gates can take advantage of superposition and entanglement to solve complex problems exponentially faster than classical computers. Quantum error correction is a method for protecting quantum information from errors due to decoherence or noise. Unlike classical error correction, quantum error correction must account for superposition and entanglement. By using redundancy in quantum states, scientists are developing techniques to build fault-tolerant quantum computers. Quantum algorithms leverage the unique properties of quantum systems, like superposition and entanglement, to solve problems more efficiently than classical algorithms. Examples include Shear's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases. Quantum algorithms promise to revolutionize fields like cryptography, optimization, and material science. Quantum cryptography uses the principles of quantum mechanics to secure communication. The most well-known protocol, quantum key distribution, QKD, ensures that any attempt to eavesdrop on a message disturbs the quantum state, alerting both the sender and receiver. This provides an unprecedented level of security, making it nearly impossible to intercept encrypted data. Quantum teleportation is the process of transmitting the quantum state of a particle from one location to another without moving the particle itself. This is achieved through quantum entanglement and classical communication. Quantum teleportation doesn't involve faster-than-light travel, but is essential for quantum communication and information transfer in quantum networks. The quantum Zeno effect is a phenomenon where frequent measurements of a quantum system can freeze its state, preventing it from evolving. Named after the ancient philosopher Zeno, this effect highlights how the act of measurement in quantum mechanics can influence the system's behavior. It has practical applications in controlling quantum systems and preventing errors in quantum computing. Quantum coherence refers to the property of quantum systems to exhibit wave-like interference effects. In quantum computing, coherence is essential for maintaining superposition and entanglement. However, external noise and interactions with the environment can cause decoherence, leading to the loss of quantum information. Preserving coherence is a major challenge in building reliable quantum computers. The many-worlds interpretation of quantum mechanics suggests that every time a quantum system is observed, the universe splits into multiple realities. Each possible outcome of a quantum measurement occurs in a separate, parallel universe. While it's a controversial interpretation, it provides a deterministic explanation of quantum mechanics without the need for wave function collapse. Quantum annealing is a quantum computing technique used to solve optimization problems by finding the lowest energy state of a system. Unlike classical annealing, quantum annealing takes advantage of quantum tunneling to escape local minima and find more optimal solutions. Companies like D-Wave use quantum annealers for tasks like logistics and financial modeling. Quantum electrodynamics, QED, is the theory that describes how light and matter interact at the quantum level. It combines quantum mechanics with special relativity and explains phenomena like the interaction between electrons and photons. QED is one of the most successful theories in physics, providing accurate predictions of particle behavior and forces. The Casimir effect is a quantum phenomenon where two uncharged, parallel plates placed very close together experience an attractive force due to fluctuations in the quantum vacuum. This force arises from virtual particles popping in and out of existence between the plates. The Casimir effect demonstrates that empty space isn't truly empty, but filled with quantum activity. Bell's theorem, proposed by physicist John Bell, shows that no local hidden variable theory can reproduce the predictions of quantum mechanics. This means that quantum entanglement and non-local correlations between particles cannot be explained by classical physics. Bell's theorem has been experimentally confirmed, strengthening the case for quantum mechanics non-locality. Quantum non-locality refers to the phenomenon where entangled particles influence each other's states instantly, regardless of the distance between them. This challenges the classical notion of locality, where objects can only influence each other through signals traveling at the speed of light. Quantum non-locality is a key feature of quantum mechanics, as demonstrated by experiments based on Bell's theorem. Quantum gravity is an ongoing effort to reconcile quantum mechanics with general relativity, Einstein's theory of gravity. While quantum mechanics works well at small scales, and relativity works at large scales, combining the two remains a challenge. Theories like string theory and loop quantum gravity attempt to describe gravity at the quantum level, potentially leading to a unified theory of everything. Quantum computing vs. classical computing. In classical computing, bits represent either a 0 or a 1, but in quantum computing, qubits can represent 0, 1, or both simultaneously due to superposition. Quantum computers leverage this to perform many calculations at once. Entanglement allows qubits to be correlated, vastly improving computational efficiency for certain tasks. While classical computers excel in most tasks today, quantum computing could outperform them in areas like cryptography and optimization. Quantum supremacy refers to the point at which a quantum computer can solve a problem that is impossible or infeasible for a classical computer to solve within a reasonable time. In 2019, Google claimed to have achieved quantum supremacy with their Sycamore processor, solving a specific problem in minutes that would take classical supercomputers thousands of years. Quantum sensors use the principles of quantum mechanics, such as superposition and entanglement, to measure physical quantities with extreme precision. They have applications in detecting gravitational waves, magnetic fields, and even changes in time. Quantum sensors are being developed for use in navigation, medical imaging, and even detecting dark matter. Topological quantum computing is a theoretical approach that uses quasiparticles called anyons to form stable qubits. These anyons have properties that make them resistant to environmental noise, potentially solving the problem of quantum decoherence. If realized, topological quantum computing could lead to fault-tolerant, scalable quantum computers. Quantum Fourier transform. The quantum Fourier transform, QFT, is a quantum version of the classical Fourier transform, used to decompose functions into their frequency components. QFT is a key part of many quantum algorithms, including Scher's algorithm for factoring large numbers. It allows quantum computers to perform operations on periodic structures efficiently, making it vital for quantum speedups. The EPR paradox, named after Einstein, Podolsky, and Rosen, challenges the completeness of quantum mechanics. They proposed a thought experiment where entangled particles seem to affect each other instantaneously, violating locality. Einstein famously disliked this spooky action at a distance and suggested quantum mechanics might be incomplete. However, later experiments confirmed that quantum mechanics accurately describes these non-local effects. Quantum dot technology. Quantum dots are nanoscale semiconductor particles that exhibit quantum mechanical properties. Due to their size, they can manipulate light and electrons in unique ways, making them useful in applications like displays, solar cells, and medical imaging. Quantum dots are already being used in high-quality TV screens, and they hold promise for future quantum computing devices. Quantum key distribution, QKD. Quantum key distribution, QKD, is a cryptographic method that uses quantum mechanics to securely exchange encryption keys. In QKD, any attempt to intercept the key alters the quantum states, alerting both the sender and receiver to the eavesdropping. This ensures a high level of security, making QKD a key technology for secure communication in the quantum era. The no-cloning theorem states that it is impossible to create an exact copy of an arbitrary quantum state. This contrasts with classical information, where perfect copies can be made. The no-cloning theorem is fundamental to quantum cryptography and quantum computing, as it prevents copying quantum information, ensuring the security of quantum systems. Quantum randomness arises from the inherent unpredictability of quantum measurements. Unlike classical randomness, which can be generated by complex algorithms, quantum randomness is truly unpredictable. This property is used in quantum random number generators, which have applications in cryptography, simulations, and secure communications. Quantum phase estimation is a quantum algorithm used to estimate the eigenvalues of a unitary operator. It's a key building block for more complex quantum algorithms, like Scher's algorithm and quantum simulation algorithms. Quantum phase estimation leverages the properties of superposition and interference to find phase information efficiently. Quantum annealers versus universal quantum computers. Quantum annealers, like D-Wave systems, are designed to solve optimization problems by finding the lowest energy configuration. Universal quantum computers, like IBM's and Google's, can perform a wider variety of computations using gate-based quantum circuits. While quantum annealers are good for specific tasks, universal quantum computers offer more flexibility and potential for future breakthroughs. Quantum circuit model. The quantum circuit model is the most widely used framework for designing quantum algorithms. It uses qubits and quantum gates, similar to classical logic gates, to perform computations. The quantum circuit model takes advantage of quantum phenomena like superposition and entanglement to solve problems exponentially faster than classical circuits in certain cases. Quantum information theory. Quantum information theory studies how information is stored, processed, and transmitted using quantum systems. Unlike classical information, which is binary, quantum information uses qubits that can exist in superposition. Quantum information theory lays the foundation for technologies like quantum computing, quantum cryptography, and quantum communication networks. Quantum machine learning. Quantum machine learning combines quantum computing with machine learning algorithms to accelerate data processing and pattern recognition tasks. By using qubits, quantum machine learning could solve problems faster than classical algorithms, offering advantages in fields like artificial intelligence, optimization, and big data analysis. Quantum supersymmetry. Quantum supersymmetry, SUSY, is a theoretical concept that proposes a symmetry between fermions, matter particles, and bosons, force particles. SUSY predicts the existence of superpartners for all known particles, potentially solving problems in the Standard Model and leading to unification of forces. While supersymmetry remains unproven, it's a key idea in modern theoretical physics. Quantum biology. Quantum biology explores the role of quantum phenomena in biological processes, such as photosynthesis, enzyme activity, and even bird navigation. Quantum effects like tunneling and coherence may play a role in how these processes occur efficiently in nature. While still a developing field, quantum biology could revolutionize our understanding of life at the molecular level. Quantum thermodynamics. Quantum thermodynamics studies the behavior of energy and heat in quantum systems. Unlike classical thermodynamics, quantum thermodynamics considers quantum effects like entanglement and coherence, which can influence energy flow and heat exchange in microscopic systems. This field has potential applications in quantum engines and efficient energy use in quantum technologies. The future of quantum mechanics. The future of quantum mechanics lies in its continued development across diverse fields like computing, communication, and fundamental physics. Quantum computers may one day solve problems beyond the reach of classical systems, and quantum technologies could transform industries like cryptography, energy, and healthcare. While many challenges remain, quantum mechanics is set to play an ever-growing role in science and technology.